This is video 16 in the series of concrete slabs. This video deals with an example of how to calculate punching shear reinforcement. In this example, we will have a slab supported by 9 columns, and the concrete quality of the slab is 25 Newton per square millimeter. The top reinforcement in the X direction, the horizontal direction, is diameter 16 at 15 centimeter center. The same for the top reinforcement in the Y direction. The bottom reinforcement is diameter 12 at 150 millimeter center. The columns have a size of 30 by 30 centimeters. The total depth of the slab is 250 millimeters with a concrete cover of 30 millimeters. And the center column, direction force in the center column is 600 kilonewton. In the edge columns, it's 300 kilonewton. And in the corner columns, it's 150 kilonewton. There is no normal force, so there is no pre-tensioning or post-tensioning effect. And we assume that the bending moment on top of the columns is 0. Determine the punching shear reinforcement at the corner, center, and edge column. We start with the corner column. The acting force is 150. The reinforcement, it's diameter 16. It's the tension reinforcement, which is the top reinforcement. It's diameter 16 at 15 centimeters center to center, so we have 6.67 bars per meter. The effective depth in the X direction is given by this formula. In the Y direction, or in the other direction, is given by this equation. So we calculate the mean effective depth of the tension reinforcement, which is the mean depth of the both layers, which is 204 millimeters. Then we calculate the mean reinforcement ratio. It's a reinforcement ratio in the X direction with the effective depth in the X direction. And then we have the reinforcement ratio in the Y direction, with also the effective depth of the Y direction. Then we take the mean of it, but it's a mechanical mean, so it's the square root of the multiplication of the two, and that's the mean reinforcement ratio. That's the new factor, it's 0.54. The maximum, that's the first step. The maximum punching shear reinforcement is given by this formula, and we arrive at 4.5 megapascal. So you can never exceed the 4.5 megapascal as shear resistance or shear force coming from the punching. The perimeter at the face of the support, which is this perimeter, it's A plus B. This perimeter is 300 plus 300 at 600 millimeters. The first critical perimeter, which is this one, at a distance 2D from the surface of the face of the column. So we have a straight portion, and 1/4 of a circle with radius 2D. It gives me 1245 millimeters from there to there. And we know that the beta coefficient for a corner column is 1.5. And now we will check the maximum punching resistance. The maximum punching shear force is then VED, the reaction force on the column, but this is given in kilonewton. That's why we multiply by 1000 to have everything in newton and millimeter. The beta corner is 1.5 divided by the perimeter at the face of the support and the effective depth. It gives us a shear force of 1.84 megapascal. The design value of the applied shear force for the corner is then equal to 0.889 megapascal, and the resisting shear stress of the concrete is then equal to the following. We first calculate the K factor, which is 1.99, must always be smaller than 2. VRD, the absolute minimum that you always can use, is given by this formula and is 0.495 megapascal. And then the resistance, the shear stress resistance of the concrete alone is the maximum of that, and it comes and it is 0.61 megapascal. Now the resistance of the concrete is 0.607 megapascal, and the applied shear force is 0.889. So this means that we need shear reinforcement because the applied shear force or shear stress is higher. The yield stress of the stirrups for shear has a maximum, and this maximum is 301 megapascal instead of 435. Now let's have a look at the corner column. The first reinforcement parameter must be at a distance S0. The last one must be within the zone S out and SKP, and S mu is the first critical parameter. So the first parameter of reinforcement, we take it as it should be between 0.3 and 0.5 D, so we take 0.5 D. Then mu out, the outermost parameter, we calculate the outermost parameter, and it is 1816 millimeters. Now we convert that to a distance S out, it's just turning around the formula, and we get S out is 774. That's the blue line from there to there, it's 774 millimeters. The last parameter of reinforcement, we used Kp equals 1.5. It should be smaller than 1.5, we take 1.5. And then you see that the SL, that's from there to there, voila. From there to there, it is 468 millimeters. The distance between reinforcement parameters should be smaller than 0.75 effective depth, and it is taken as 153 millimeters. Now we can calculate easily the needed number of parameters. Just remember, we need at least 2 parameters. You always have to make 2 parameters at minimum. So we calculate the total number of parameters needed, and we have now in total, we see that we need 3.4, and that means 4 parameters of reinforcement. So that's what we need. We need 4 parameters of reinforcement. The stress of the punching reinforcement is 300 megapascal. The reinforcement for each parameter, per parameter, is given by ASW1 with the formula that we have seen in the previous slides, and it's 182 square millimeters. The tangential spacing of the rebars depends on the position of the parameter. If this position of the parameter is within 2D, then the tangential spacing is 2D. If the perimeter is further away than 2D, then the tangential spacing must be smaller. That must be smaller than 2D, must be 1.5D. So it means that in the first perimeters you have 1.5D distance, and afterwards it can be 2D. So now we have to check every parameter, and there are a lot of parameters that we have to choose. So the first parameter that we have to choose is where do we put the first parameter, and we said we are going to put it at 0.5 times the effective depth, so that's at 102 millimeters. We calculate the total length of that parameter at S0. Why? Because we need to determine the maximum and minimum distance of each reinforcement alongside this parameter. So this is 760 millimeters, and now we have to choose a diameter. On this diameter, there are some limitations. At least you must put enough rebars to obtain ASW. You must have a small enough diameter so that the distance between the reinforcement, the tangential distance between the reinforcement must fulfill a certain criteria. So now if you put that in a simple formula, and we take, for instance, as a minimum diameter of shear reinforcement 8, then you will see that depending on this term gives you the minimum amount of rebars 8 that you need to fulfill ASW, and this gives you the distance, the amount of bars you need to fulfill the tangential distance. And you will see that we have 3.6 bars, so we need 4 bars within that first perimeter. And if you have 4 bars, we can calculate now correctly the tangential distance of the first perimeter, which is μs null divided by the number 4. It's 180, so that's okay. So this means the first perimeter of reinforcement is situated at 102 millimeters from the face of the column. It's a diameter 8. We got 4 diameters 8 with a center-to-center distance of 180 millimeters. This is not all. Now we have to check the minimum diameter of reinforcement used. It must fulfill at a certain minimum diameter, must fulfill this equation, and it should be at least 4.4 millimeters. So that's no problem because we have 8, which is bigger than 4.4. Now we take the second perimeter of reinforcement. It's the first one plus the radial distance between the perimeters, and we have 255 millimeters. The total length of that second perimeter is 1000 millimeters. Again, we choose the diameter, we choose 8, we need 3.6, we make 4, and we check the minimum required diameter of shear reinforcement. And then it's a repetition. We look for the third reinforcement perimeter, which is the first plus, again, the distance SR, the tangential distance between the two reinforcement perimeters. This is the total length of the reinforcement perimeter. Again, we choose 8, we arrive at 4, and the minimum diameter is now 5.6. Then the fourth perimeter, we do exactly the same procedure. You will see that the minimum diameter increases all the time, but still it's 6 and we have chosen 8, so that will be fine. Then we check the second perimeter, the second critical perimeter. The first one we've checked now for radius equal to 2d. Now we will check the radius 4d. So you will see here 2 times 2d, that's 40. So this critical perimeter is 1882 millimeters. We calculate the shear force of the shear stress, the shear of the punching shear stress, the punching stress, which is 0.586, but this is smaller than the punching shear stress for resistance given by concrete alone. So we don't need reinforcement, punching reinforcement in the second perimeter, second critical perimeter. We can make now a little drawing. This is the S0, S1, S2, S3, and S out. And you see now for S out, that is where outside S out, we don't need any reinforcement. And the last perimeter, S3 of reinforcement, must be situated between the SKP, which is 1.5D, 1.5D distance from S out. So the last perimeter must be inside there. This is the green one is the critical parameter, the first critical parameter, and then you have the two reinforcement parameters inside it. This is the summary of all the calculations done. The effective depth of the slab was, the mean effective depth of the slab was 204 millimeters. And then the resistance of the concrete to shear in stress, expressed in stresses, is 0.607. The maximum is 4.5, and the applied shear stress is 0.89. And then you have all the results of the calculations. Then we make a little drawing, and you will see the first, second, third, and fourth parameter, and each parameter has 4 diameters 8 evenly spread out over the parameter. And if you make a cross section to it on the side, then you will see it will look more or less like that. So this is how we have determined the needed shear reinforcement for a corner column. We can now do exactly the same for the edge column. So we go through it much quicker. It's a repetition of what we have done before. The difference now is that the first parameter has a different shape. If you make the little drawing, then you can easily calculate the first critical parameter. We do again the different calculations, what is needed. We look for the resisting shear stress, which is the same as the previous one, of course, it's the same concrete quality. So you have 0.607 megapascal. And we see that we need shear reinforcement in the first critical parameter. And then again, we follow the procedure for finding out how much reinforcement parameters do we need. For that, we calculate the outer parameter, and we can calculate from there on, we can calculate how much parameters do we need, and we also need 4 reinforcement parameters. Then we calculate the reinforcement needed per parameter, that's 361. And then again, after that, you have a lot of combinations possible. You have to choose the reinforcement diameter to fulfill ASW and to fulfill the maximum spacing of reinforcement. It's a repetition. Of course, I've only put in here the final result. And you see that now we need 4 diameters 12 as punching shear reinforcement. For the second parameter of reinforcement, we need 6 diameters 10. And for the third, also 6 diameters 10, and the fourth, 7 diameters 10 reinforcement. If you use a diameter 12, then the spacing becomes too high. That's why we choose here for diameter 10. And then we have also to check the second parameter on the distance 4D, and in the second parameter it is okay. We have an applied shear force or an applied shear stress of 0.59, and the concrete can resist 0.61. So no shear reinforcement is needed in the second parameter. Again, we give a summary and a drawing, and you will see on the drawing that we have 4 parameters of reinforcement, and the first parameter has 4 diameters, and the second parameter has 6 diameters, and so on. And then you can make a little sketch of denoting where the reinforcement must be put. The center column, the same procedure for the center column. The center column has, of course, the first parameter that looks like the little drawing there. And again, we check the shear stress, or the shear stress resistance of the concrete alone. We know that 0.607 is, and the applied shear stress is 0.899, so shear reinforcement is needed. Again, we put the first perimeter at 0.5D, then we look at the outer perimeter, and we put the last perimeter of reinforcement as 1.5D. So remember that the 1.5 is chosen by the designer. It must be smaller than 1.5, but you can use 1, you can use 1.2, 1.3, 1.4, and so on. The same happened to the first perimeter. You must have a figure between 0.3D and 0.5D. So that's why it's in yellow. You choose this value. And then the distance between the reinforcement parameters, and from that you can see that we need at least 3 perimeters of reinforcement. If not, then the distance SR becomes too big between the 2 perimeters. We calculate the needed reinforcement per perimeter, which is 565, and then again for each perimeter we look for a suitable combination of diameter and number of diameters. We check the second perimeter on the distance 4D. We see that the applied shear stress is 0.5 and the resistance is 0.6, so there's no punching shear reinforcement needed in the second perimeter. We have the summary here and a little drawing showing where the reinforcement should be put